we will see a chapter of organic chemistry, that is haloalkanes, which are the derivatives of alkanes and arenes. In that, we will focus on physical properties of haloalkanes. In that, we will see the first physical property, that is the bond strength and the bond length. Before that, we need to know what is the CX bond. Here C stands for your carbon, whereas X stands for your halogen atom, which could either be chlorine, bromine, iodine or fluorine. For our example, in order to understand this concept, we will consider the example of CF and CBr. That is the bond between carbon and fluorine and carbon and bromine. If we look at the periodic table, in that the position of fluorine and bromine, if you take it into consideration, fluorine is higher up higher at the level in the periodic table compared to that of bromine. So we can say that the atomic radius of fluorine is smaller compared to that of the atomic radius of bromine. Now this size of an atom, which is the atomic radius, plays a very important role in this bond strength and bond length. What it says that as the size of your atom goes on increasing from fluorine to iodine, what happens is the strength of that atom goes on decreasing. So we can see that because the length of this bond of CF is smaller, its strength is much more than that of the CBr bond. Now we will come to the hybridization taking place at this C, that is carbon. It's an Sp3 hybridization. So this Sp3 hybridization, in that there is an overlap of your p orbital. If you compare the overlap of carbon and fluorine and carbon and Br, bromine, we will see that the overlap in Br is very much smaller compared to that of the overlap of the p orbital in CF bond. Due to that, the strength of this bond, CBr bond, goes on decreasing. If we take a clear study of, for an example, we will consider methane, and we will replace every hydrogen by an halogen. We've considered an example right here. This will give us a clear idea of how the strength and the length of the bond is affected by the size or the atomic radius of an atom. So if you consider for methyl fluoride, the bond length is the minimum. It is measured in Armstrong, and whereas the bond strength is maximum for methyl fluoride. As we move downwards towards methyl iodide, the bond length goes on increasing and it is maximum at methyl iodide. That is, it says that if your halogen is iodine, in that case your bond length is maximum. Whereas the bond strength goes on decreasing as we move from fluorine to iodine, and it is minimum at methyl iodide. Under physical properties, we will see now the polarity of the CX bond. We will see why is it called a polarized bond. For that, let's consider the CX bond, in that the carbon and halogen atom develop charges. This halogen is highly electronegative compared to the carbon. So it develops a partial negative charge, say as minus delta, whereas the carbon develops a charge as plus delta. Due to these two charges being developed on the carbon as well as the halogen atom, what happens is that being positively charged, the carbon is subjected to an attack of the nucleophilic species or the anions. Whereas the halogens being negatively charged or being developed by a partial negative minus delta charge, what happens is it will be attacked by the cations or the other electron deficient or we can say as positively charged species. Now because of this, we can come to a conclusion that because of this negatively or highly negative or highly electronegative charge developed on this halogen, we can say that this bond between carbon and halogen that we call as CX bond is highly polarized. The next physical property we will be seeing of haloalkanes is the boiling point and versus the corresponding alkanes. The corresponding alkanes, first we will see what is this corresponding alkanes. For example, consider methane. What happens here is there are 4 hydrogen present. If we start replacing the hydrogen, if we replace one hydrogen by an halogen, that can be called as the corresponding alkane. Now, in order to study this boiling point, we will compare the 3 methane, methyl fluoride and methyl iodide. As the values mentioned here, if we see, considering the first 2, if we see, we will find that the boiling point of methyl fluoride is much more as compared to that of methane. Now why is it so? What happens is, since it is a liquid solution, the intermolecular forces as well as the polarity leads to the formation, or it lets it through a dipole-dipole attraction. As considering an example of methyl fluoride right here, as seen, it develops a polarity of minus delta, whereas carbon develops a polarity of plus delta, and there is a formation of the CF bond here. Now since it is a liquid solution, there will be many such more bonds being formed. Considering 2 such bonds, we will find that this minus delta partial negative charge will be attracted by this positive delta, which will be formed on this carbon atom, and there will be a bond formed as shown by the dotted line here, which is nothing but the dipole-dipole attraction. Due to this dipole-dipole attraction, we can say that the boiling point of fluorine or the halogen or this methyl fluoride is much more compared to that of methane. Now, taking in consideration the comparison between methyl fluoride and methyl iodide, if we see here, we will find that methyl iodide, the boiling point is much more than that of methyl fluoride again. Now why is this increase in the boiling point? This increase is, if you go to see in the periodic table as mentioned before, yes, iodide lies below that of fluorine. That means the atomic size of iodine is much more as compared to that of fluorine. But is this the only case? No, it is not that. The main reason for this is that as the atomic size increases, there is a London dispersion force, which is nothing but this force is the intramolecular force. Because of this force, the boiling point of methyl iodide is much more than methyl fluoride. So we can say that as the atomic size increases, its London dispersion force is increasing, and because of that the boiling point is also increasing. Under haloalkanes, after seeing the properties which are the physical properties of haloalkanes, we will move towards the chemical properties of these haloalkanes. In that we will discuss about the substitution and the elimination reactions. Firstly, we will see the elimination reaction. For that, we will consider an example of an alkyl halide which is reacted in presence of a basic solution of potassium hydroxide in an alcohol. Now what happens here is, due to the reaction, there is a formation of an alkene. In elimination reaction, there is a selection to be done because there are 2 products being formed, that is a major product as well as a minor product. So we need to select one of the products, whether the major or the minor products. Now what happens here is, this hydrogen which is attached to the carbon, it is removed along with this bromine halogen, and there is a formation of a double bond here. Now there is another possibility that this hydrogen right here connected here to this carbon can also be removed along with bromine. So in that case, the formation of the double bond will be towards this side. So there are two mainly products. One is the major product of alkene being formed, whereas the other is the minor product. Now how do we decide which is the major and which is the minor? So in this elimination reaction, the product which is more stable forms the major alkene product. The next reaction which we will be seeing is the nucleophilic substitution reaction. Nucleophilic substitution reaction, as the name suggests, there is a nucleophile which is reacting with this haloalkane, that is the alkyl halide. For our example, along with this alkyl halide, we have considered the cyanide nucleophile. This nucleophile, what happens, the substitution reaction is that this halogen right here is substituted or is just replaced by the cyanide group. Now this nucleophile could be any of the, you could have an hydroxide group, SH group or NO2 group according to the reacting nucleophile. So as the nucleophile being used in your product or as the nucleophile be reacting in your product, so is the product being formed as the result. So the general expression for this substitution reaction with an alkyl halide will be represented by in this form. There will be some nucleophile which could be anything. It could be either a cyanide group, hydroxide group, a SH group or NO2 group. So this will be your nucleophile. It will react with your alkyl halide and it will result in just substituting this halogen with the nucleophile and you will get some end product. Now we will see some examples on this nucleophilic substitution reaction as we have studied before. These reactions are also known as the SN reactions. For example, we consider propyl bromide. This alkyl halide, we are reacting it with a set of nucleophiles. Consider the first case where your nucleophile is potassium cyanide. The charge on potassium is plus whereas on cyanide is negative, as we know. So this undergoes a substitution reaction and the product formed is alkyl cyanide and there is some end product as potassium bromide. Now if you consider the reaction, the same reaction, but you have replaced this potassium cyanide with silver cyanide. Now what happens here is the product now formed is slightly different. Instead of an alkyl cyanide, there is a formation of isocyanide. Whereas the same reactions take place with potassium nitroxide and silver nitroxide and we get alkyl nitrite and nitroalkane. Now when your nucleophile of potassium cyanide is reacting with your alkyl halide, now what happens is this potassium cyanide is predominantly ionic. So it releases the cyanide ions in the solution. Now these cyanide ions, they are highly nucleophilic substances and because of that they combine or bond at the carbon side and there is a formation of a major product. Whereas in case of silver cyanide, what happens is it is a covalent, it is highly covalent, so there is a formation of a major product as isocyanide and that's why these two products formed are different. Similar to potassium cyanide, the reactions with KNO2 and AgNO2 also give us two different set of products, which is alkyl nitrite and nitroalkane. Vinyl chloride is less reactive with these nucleophilic substitution reaction. This is because they are less resonant. Under nucleophilic substitution reaction, that is the SN reactions, we will see the two types, that is the SN1 type and the SN2 type. The SN1 type is the unimolecular nucleophilic substitution reaction. This reaction takes place in 2 steps and it is the first order reaction. This reaction has the order of reactivity, like the third order reaction is more reactive compared to the second and the first order for alkyl halides. The next is the SN2 reaction. The SN2 type of reaction is a bimolecular nucleophilic substitution reaction in which this type of reaction takes place in 1 step and it is the second order reaction. The order of reactivity for alkyl halides to this SN2 type of reaction is the first order reactions are more reactive compared to the second and the third order reaction. So this is mainly the main flow of mechanism of the nucleophilic substitution reaction, or we can say the chemical properties are based on these 2 types of mechanisms.